All right, so this video is going to be all about the cross product, and so I'm sure you guys have been finding that part of the reason why torque and angular momentum is difficult is because of the cross product. And what I'm going to do is I'm going to build this up from our understanding of the dot product, and then we're going to understand it in its more fuller detail, because at the end of the day, the dot product and the cross product are two ways that you can multiply vectors together, and they complement each other pretty well. So what I have here in these two pictures are examples of when you would use a dot product and when you use a cross product. So we remember from the work-energy theorem that the work, or the net work, done on an object is going to be equal to the integral from R1 to R2 of F dot dr. And this is going to be equal to the change in kinetic energy. So the reason why I bring this up is so that we can talk about this in the context of the physics. So when we're taking a dot product in the work-energy theorem, what we're trying to find is how much of the force is in the same direction as the direction that we're moving. Because at the end of the day, if I take this free body diagram that I have here, or this block on this inclined plane right here, and I draw the free body diagram, then we could see all of these forces acting on here. So we have the normal force, we have the force of gravity, and we have this applied force. So when we want to think about what's changing the kinetic energy, it's only the forces or the components of the forces that are parallel to the plane. So for instance, we don't want things that are perpendicular. So the normal force is an example of a force that's perpendicular to the plane, and this isn't going to change the kinetic energy. So when we're using the work-energy theorem, we're interested in the portions or the vector components that are going to be parallel to one another. Whereas when we're looking at the cross product, or when we're talking about torque, we're interested in the components of vectors that are perpendicular to each other. So here I'm drawing this vector r that's representing the distance vector that points from the point of rotation to where the force is acting, and F is perpendicular to it. So torque is maximized when these two are perpendicular to each other. You'd never be able to turn a wrench if what you do is you take the force and you apply it like this, right? Because that's parallel to R. We need what's perpendicular. So when we're talking about the dot product, and consider just two generic vectors here. So we'll have some vector. Here's a coordinate axis. We have some vector A and some vector B like this. And there's going to be some angle of theta in between them. Okay. So when we want to take the dot product, there were two ways that we could take the dot product. So we want to do A dot B. The first way that we could take the dot product was to say that this was going to be equal to the magnitude of A times the magnitude of B times the cosine of the angle in between these two, okay? So here, that angle is explicitly given, but if it was a different angle in the statement of the problem, so say I was given that angle, I call that one theta, or this angle, call that one theta. You need to figure out what the angle is in between. So that's also going to be important with the cross product, okay? So this was one way to define the dot product. I'm going to draw another picture here so that I can break my vectors and components and color this so you guys can see it a little bit better. So here's my vector A, and here is my vector B. Okay. Now I could break this into components. So I could say that there is some amount of this vector B that is like this. So there's some B. This is some by. Okay, so that's the y component. And there's some x component. We can say that this is going to be bx. So b is broken into components now. And a could also be written in components. So here I have some ay, and here I have some ax. Okay. So the other way that we could take this dot product, and you can see that if you work through some calculations, that these are the same thing at the end of the day, that you could write A dot B if you have A and B written in components. So let's explicitly write these in components. So we have, and we use this for our cross product as well. So we have A vector so A vector is going to be equal to AX x hat plus AY y hat. Okay, and B vector b vector is going to be equal to bx, x hat, plus by, y hat, okay? So if we want to take a dot b the other way, what we do is we say this is going to be equal to ax bx plus ay by, okay? Now, likewise, we could look at the cross product, and there are two ways that you can take the cross product. And depending on the situation, one is going to be more advantageous to the other. We'll see when I solve some of those problems that I gave you in class, that depending on the situation and the information given, you are going to want to evaluate the cross product a different way. So here's our cross product. If I wanted to give this table a heading, I would call it the way to multiply vectors. You have the dot product, you have the cross product. So when I take the cross product, we use this x symbol to denote the multiplication. And the way that we've been using this so far is we say this is the magnitude of A times the magnitude of B times the sine of the angle between them times this unit normal vector, where this unit normal vector is determined. So this is, let me use a different color here, which shows up well. I think this one does. So this is the unit normal vector. And by definition, this vector is going to be mutually perpendicular to A and B. Okay, so I'll talk a little bit more about this. The way that you determine this is by applying the right-hand rule. Okay, so that's one way to take the cross product. And we can see that that one's kind of equivalent to the one that we have on the first line with our dot product here. So these guys are like the same. And there is an analogous way to take the cross product if we have this vector written in components. And that is going to say that this is going to be equal to ax by minus ay bx times some z hat. So x and y are the two coordinate axes that I have here. And the coordinate axis that is mutually perpendicular to both of those is the z direction. Okay, so you could draw this in 3 dimensions, if you like. So the way that you typically do this is you say that this is the x direction, this is the y direction, this is the z direction. Okay, so this is the z direction, and you can see then that z is mutually perpendicular to x, y, and z, and each one of these has their own unit vector, right? So we have some unit vector x hat, we have some unit vector y hat, and we have some unit vector z hat. Okay, so this is another way that we can define the cross product. So in some of the coming videos, I'm going to show you exactly how we're going to use this other definition. And the reason why you want to use this definition is ultimately it comes down to the fact that when you're defining unit vectors, you define them to be perpendicular to each other, right? So we say x hat and y hat, those are perpendicular to each other. Z hat is perpendicular to both of those. And so the virtue of defining your unit vectors to be perpendicular to each other has to do with the fact that you can kind of cycle through the cross products between them. And if you have the cross product of 2 of them, you're going to get a third. And if you have a cross product with one of them, with itself, it's going to be 0. So let's see that in action here. We'll apply it for its definition to show that this is true. So what would x hat cross x hat be? Well, we can look at our definition that we have on the first line here, and the magnitude of the 2 unit vectors is 1, right? Unit vector means that it just carries direction. It doesn't carry length with it. It has a length of 1. So these 2 magnitudes here are going to be 1 times the sine of the angle between them. Well, I have 2 vectors pointing in the same direction. The angle between them is going to be 0. And so this one is going to be 0. We could say, well, what is x hat cross y hat? Well, it's going to be 1 times 1 times the sine of the angle between them, which is 90 degrees, times the unit normal vector that is mutually perpendicular to both of them. That one's going to be z hat, according to the right-hand rule. Now, something you could ask yourself is what is y hat cross x hat, right? And this is where the right-hand rule becomes important, because what we're doing to determine n hat, we take our fingers and point them in the direction of the first vector. So say, for this particular example, I'm going to take my fingers and I'm going to point them in the direction of x hat, and then I curl them towards y hat, and my thumb is pointing in the direction of the third vector. Okay, so that's why we can see that this one's going to be the plus z hat direction. But let's consider what happens when we have y hat cross x hat. So we take our fingers and we point them in the direction of y hat, and then we orient our hand in such a way that we can curl our fingers in the direction of x hat. So you see how now my fingers are pointing in the direction of y hat, and to curl towards x hat, my thumb is going to be pointing down. Okay, so this says that this is going to be minus z hat. Okay, and you can go through all of the permutations of this, so you can see that x hat cross z hat. Well, we take our fingers, we point them in the direction of x, and then we curl them in the direction of z. So this one is going to be. So now we want to think about what is y hat cross z hat. So y hat cross z hat we can determine by taking our hand and pointing it in the direction of y hat, and then curling our fingers in the direction of z hat. And so here, this is going to be pointing in the x hat direction, right? So this is going to be x hat, okay? So there's our cross product. And we could see, analogously, if we want to take the dot product between these vectors, we have x hat dot x hat. This is 1. X hat dot y hat is going to be 0. Y hat dot y hat is going to be 1. Because again, when we're thinking about what is the cross product doing, what is the dot product doing? The dot product is kind of pulling off the terms that are the same direction. The cross product is pulling off the terms that are perpendicular to each other. And ultimately, that points all the way back to the physics, because what we want when we're getting the dot product, and the way we use it with work-energy theorem, we want the force that's in the direction of motion, and not the force that's perpendicular to it. Whereas when we're talking about torque, we want the force that's going to be perpendicular to some r that's pointing from a point of rotation to where that force acts. Okay, so that's it for just a little bit of an overview of how we use this dot product and cross product. But for the folks that are working on the teams assignments right now, there's something else that you can do with this, because I never said you had to work with x hat and y hat. You can work with r hat and theta hat too. So if I have r hat cross r hat, and let's draw our coordinate system here, and remember the way that we defined r hat and theta hat. These are themselves perpendicular to each other. R hat cross r hat is going to be 0. Unit vector cross with itself. R hat cross theta hat, on the other hand, this is going to give us a z hat, right? Because in reality, what we're doing here when we're drawing this coordinate system, I'm calling this an x and a y. So you have to think about how I'm moving this around and I'm rotating it. But here's my x and here's my y now. I'm drawing it in 3 dimensions. Okay, and then here's my r hat, and here's my theta hat, right? So I kind of took this and flattened it out, and then turned it around, and now I have my z pointing up. So if I point my fingers in the direction of r hat, and then I curl them towards the direction that theta hat is, then my thumb is going to be pointing upwards, which is going to be z hat direction. And the other case is going to be theta hat cross r hat is going to be minus z hat. Okay. Now, why do I mention this, and why is it useful for the calculation that you guys are doing? Well, I give you v vector, and I'm not going to write out the whole component, but I have v vector is going to be v sub r hat plus v sub theta times theta hat. A vector is going to be a sub r hat plus a sub theta times theta hat. And I also tell you that the angular momentum, L, is going to be equal to r vector cross p vector, and the torque is going to be equal to r vector cross f vector. Okay. And the other thing that we need here is that r vector is just going to be equal to the magnitude of r times r hat. I didn't mention that explicitly, so that's probably going to help. So now what I want you to do for this calculation is I want you to prove, that tau vector is equal to dl dt. Okay. So the way that you're going to do that is you're going to take this, evaluate the cross product by saying the sum of the forces, or the force, is going to be equal to the mass times acceleration. We have the acceleration vector here, and then we can put that on the left side, right? So I'm going to take this and I'm going to plug it in there. Okay. So then what I'm going to have is the torque. This is going to be r vector cross f, right? Because I just replaced that, is equal to d by dt of this is d by dt of r vector cross p vector. Okay, and I'll write one more step here so you guys really have this very explicitly. So then you're going to say that f is equal to ma, p is equal to mv. Okay, so then I can replace this. This is going to be r cross ma is going to be equal to d by dt of r vector cross mv, and we can actually cancel our masses. These are constants, so they don't come into play. So at the end of the day, what I want you to do, I want you to use the things that I told you here, and explicitly what I give you for v sub r, v sub theta, a sub r, a sub theta, and these rules that I laid out for the way that the cross product works, to show that this equality holds, that this is indeed true. And effectively what you're doing then is you're proving that the torque is going to be equal to the time derivative of the angular momentum. So that's going to be it. I'm going to do a couple more videos before I head home, but I hope you guys enjoy. And if you have any questions, as always, just ask me in Teams.